Good afternoon. Thanks to Gabe and Alex and all the organizers on the research paper, I guess for picking my paper. That's something to thank them for. I'm appreciative there. So we're going to be talking today about total hockey rating. Should mention my co-author, Jim Curo. And this was really a part of Jim's senior thesis at St. Lawrence. We sort of added to it and built it up a little bit to get our total hockey rating. So those of you with a little bit of knowledge about hockey, a lot of the metrics that we have, so the traditional ones of plus minus or points, are really about things that happen on the ice and not things that are prevented from happening. And so what we wanted to do was try to get something that was a little bit deeper. There's some more advanced ones. We've got Corsi numbers up here on the board. We've got GVT, which is from Hockey Prospectus, and Delta SOT, which I didn't mention in the paper, but was pointed out to me since. And then last year at this conference, Brian McDonald presented an expected goals plus minus. Again, sort of trying to get at more and more sort of the things that are happening on the ice that are of value, and not just in terms of scoring goals, but also in terms of preventing. So the goal of THoR is really to try and get at what is the value for the plays that happen. We know there are valuable plays that aren't part of plus minus or that aren't part of points. Things like keeping that puck in the offensive zone on a 50-50 and getting that loose puck and chasing it down in the neutral zone. Those sorts of things, and trying to get at a way that we could measure those. Now, we're not going to directly measure those, but we're going to have some proxies that we think are outcomes of those events. So what we want to do is we value every play. We're going to do and focus in this paper on even strength. So go ahead and mention that now. The results that I'm going to show are even strength. We have another model for power play and penalty kill that we can talk about at a later date. We want to account for the other players that are on the ice with you, both for and against. Want to account for zone start, which is where your shift begins. So we know from recent hockey analytics literature that where your shift starts has a big impact on the amount of points and the goals that are generated, and we also want to account for home ice. So we're going to use the RTSS that's generated by the NHL. Okay, they record a bunch of things: shots, goals, misses, block shots, end of period, all those sorts of things into a play-by-play file. Okay, we also get from that players on the ice, and for shots we get the X and Y coordinates. Okay. Now, having said that, this system is rich. We're going to have a lot of data. We're going to end up with 500,000 plus observations. Okay. But we've got some issues with the quality of that data. We know that we've got some measurement error in that data, and we're going to try and do our best to account for that, particularly for things like X and Y coordinates. Madison Square Garden is well known for having bad X and Y coordinates, for example, among other things that happen at MSG. Giveaways and takeaways, we know that those tend to be biased. That is, the home team ends up with more takeaways than are not credited with giveaways. So giveaways happen for the away team. There's some question that's recently been raised about face-offs. We won't actually address the face-off issue here, but something around 5% of the face-offs end up being incorrect in some way. We also know that there's a bit of a bias from hits. And so we have this rink-to-rink variability that we're going to try and deal with. So in the hockey analytics literature, the sort of worst thing that's out there right now, I guess the worst in my opinion, is the X and Y coordinates for shots. It receives a lot of attention, and it is quite bad. So what we decided to do is make an adjustment here. Basically what we do, okay, is we look at the distribution of shots taken by the away team at a given rink, and then we look at the distribution of shots for all away teams at all rinks, and then we can get from that a rink adjustment. Now, the fancy bit of math that we have going on here is we're making that adjustment in the probability distribution function. Okay? So we're looking at changing that distribution function and making an adjustment. So a shot that is 17 feet in Boston, we might adjust that to be a shot equivalent at 19 feet in Calgary. Okay? So we can get that kind of adjustment, again, trying to get those X and Y coordinates more systematically correct, and getting rid of the relative bias. There's obviously some absolute bias, but in terms of what we need here, we want to get rid of the relative rink bias. Other adjustments that we made in terms of takeaways and giveaways, we turned that into a turnover. Okay? We turned that into a single value for a turnover, and so we didn't get into the giveaways and takeaways, and we hope to get rid of some bias there. We got rid of all the events that didn't involve some sort of an action. Okay? And so we're left with the 8 events that are there: goals, shots, missed shots, block shots, hits, face-offs, penalties, and turnovers, which is our way of sort of concatenating giveaways and takeaways. We have 2 full seasons. That is in part due that we want to get rid of any sort of small sample size issues, though we will have some players that have very, very few plays, and we will deal with them. But we've got about 510,000 events that go into it. So the next thing that we had to do, once we sort of cleaned up the base data, is to come up with a value for each play. And so our idea here is that we'd like to say, what does that play do in terms of leading to a goal? Okay? So the metric that we came up with here, right, is a net probability, okay, which is the probability that the home team scores after that event minus the probability that the away team scores, okay, in a given amount of time. So the idea, we start with k seconds. We looked at values for k from 5 to 50. What we saw was stability happens after about 10 seconds. That is, after 10 seconds, what had happened is not affected by when it went on before. We were a little bit conservative, and so we went to 20 seconds there. Okay? The other issue that we know about, right, is that you have scoring rates, that is the probability of a shot becoming a goal, seems to have a lot of short-term fluctuation. And we'll address that in just a second. But that's not another reason for doing and getting at these events with what we're going to call the NP20. So net probability 20. Okay? We made, after doing all that and getting those events, we made a couple of tweaks. One is to a penalty. Right? A penalty obviously has a big impact on the game, and so we wanted to address that. And so what we did is, for the team that drew the penalty, okay, we wanted to reward them, or the team that took the penalty, we wanted to penalize them. And so the penalty here is the length in minutes, so a 2-minute penalty, 5-minute penalty, times the scoring rate per minute. Okay? So we've got that. And the other thing that we did is that we wanted to make shots have NP20, but we also wanted to include the probability that a shot ends up being a goal. Okay? So both shots and goals, we gave the probability that a shot, given its x and y coordinates, okay, its adjusted x and y coordinates, as well as the shot type, ends up being a goal, plus then the 20 seconds after if it was a shot that didn't end up being a goal. Okay? To do the location, and again, to adjust for some of that measurement error in the x's and y's, what we did is not take the exact xy location. We ended up gridding the ice, and we end up with 57 locations, one behind the goal, 54 in the offensive zone, so we broke the offensive zone into 54 sort of grids. Then we've got a neutral zone and a shot taken from the defensive zone. Okay? So we have those probabilities, and we have it for each shot type. Okay, a couple of examples here of what we end up with NP20. And what I've got here is I've got the marginal rate for those shots. So basically what I've done is averaged over the x's and the y's here. Just otherwise, I'd have a table that ran on for pages and pages. Okay? So for example, that a backhand shot gives us an NP20 of about 13%. So there's a 13% chance, or a 13% net probability of a goal in the next 20 seconds for the home team if they take a backhand shot in their offensive zone. Okay? The home team gets a turnover. That is, the turnover goes to the home team. Okay? That's about a 4% net probability there. Okay? We can see that shots are going to be our most valuable events. Okay? We're going to have turnovers in the offensive zone, face-offs. Again, if you were here last year, face-offs a bit of an issue at the hockey panel. Okay? Not a whole lot of value there in those face-offs. And again, hits, and as Brian McDonald has shown us, hits sometimes having a negative effect on goals. And again, that's because hit represents the fact that you don't have possession. Okay? So we've got that NP20. And then we're going to build it into our regression model. So we're going to regress that NP20 onto a mean effect, which is effectively going to take the place of home ice. Then we have the effect of the players on the ice for the home team. minus the effect of the players for the away team. So the NP20, right, is home probability minus away probability. And so then on the right-hand side, you're going to have home players minus away players. Okay? And that is so that if we end up with negative NP20, we're benefiting the away team. If we end up with positive NP20, we're benefiting players on the home team. And then we've got our zone start effect. So as I mentioned earlier, an effect for starting in the offensive zone or starting in the defensive zone. Okay? We left goalies in, so goalies are actually part of this model. Okay? But we haven't paid much attention to them because we're really treating them as those are the team effects. Okay? So we're going to take the sort of overall team effect and how do you do relative to that. Okay? The results that we get, okay, some rating for each player. What we do, and that's a rating per play, we take that and multiply it by about 67 plays, okay, per game, which is about a third of what happens at even strength. Again, we're focused on even strength here in this talk. Okay, 67 plays per game, 82 games, and then we divide by a goal differential. It's been shown by several people. A goal differential of 6 is worth an extra win. It's worth 2 points in the NHL. So what we then get is sort of a wins over average, okay? And that gives us the values at an equal number of plays, okay? Before we get into player results, talk about zone start. So what we have for zone start is if you move from your neutral zone to the offensive zone, it's the equivalent of taking an average player on your line and replacing them with a top 5 player. It's that big of an impact to start in your offensive zone versus starting in your neutral zone. Okay? If you say that you take all shifts in the offensive zone for a game, it's worth about a half a goal. If you take 10 additional zone starts per game, that turns out to be a little about 5.5 goals per season. Okay? If we look at the home ice effect, it turns out to be about a third of a goal per game. Again, taking the per play, extrapolating up to per game. And what we find for these 2 particular seasons, and we've done this for 10, 11, 11, 12 seasons, is that works nicely and is very similar to some other estimates that people like Sagarin have gotten for what is the effect of home ice. Okay, so here are, based upon 10, 11, 11, 12, top 15 forwards, based upon this system, okay, where we extrapolate out, assuming everyone played the same amount. Okay? Now, lots of good and familiar names, a couple maybe not so familiar. So 2 things to point out, maybe 3. Alexander Steen was probably a bit of a surprise there. His Corsi relative numbers, so if we think about Corsi, which is the percentage of total number of shots, block shots, and missed shots that your team takes relative to the total, for Steen is incredibly high. So Steen is not a surprise here in terms of what we get. Tyler Kennedy there in third is quite a surprise. So here, now I'm going to go ahead and maybe refute Brian Burke's comment that statistics are really for support and not illumination. I think Tyler Kennedy's case is one where we actually learn something here. I'm going to catch a lot of flack for Tyler Kennedy. I've already done it on the web quite a bit now that this paper is public. Okay? What we do know, though, right, and sort of investigating why this happens, is Tyler Kennedy is one of the best players in the league at getting shots per time on the ice. Okay? 2 years ago, 2.5 years ago, or for the 10-11 season, he was one of the top 6 players in the league in shots per time on the ice. Okay? Last year, he comes in about 22nd. So when Tyler Kennedy is on the ice, he's getting a lot of shots, and shots are what is leading to value here. Okay? So based upon the model that we've got, right, we get some value there. The other names I think are less surprising. Sidney Crosby at 15 is a bit surprising. But one of the reasons for Crosby, and we'll talk about this in a bit, is what we do to get rid of some of the small sample size effect is we do a bit of shrinkage, statistical term there. We're using a ridge regression. But it basically means I'm taking my estimates, and in terms of predicting future performance, we're taking them and shrinking them towards 0 by a little bit. And Crosby, because effectively he's only played 1 season out of these 2, gets shrunk a bit. Had he played the full 2, he probably comes in about 5th or 6th. Defensemen here. Again, I'll just note one thing here in making the comparison there, more interest generally in forwards, but you'll see that the value for the top 15 forwards a good bit more than what we get for defensemen. And that tends to be true throughout the ratings, that we're seeing, right, that forwards are giving us more wins created, right, on sort of our metric here of wins over average, wins created, than we're getting for defensemen. Okay, a little bit talking about sort of the reliability of using these sort of systems. So first, we based everything upon those 8 types of plays there. Here are 3 years from the NHL's RTSS, and basically the distribution of those events going across. We've got a fairly stable system. Now, this doesn't include last year, because when we made this graph, it wasn't completed, but expect to see something similar there. The other thing that we did in terms of reliability is we looked at what happens when a player is traded. So in our database, right, when a player is traded, they're actually treated as a different player in our model. Okay? And so what we did is we said, well, what is the difference between those 2 ratings? Okay? We'd like that difference to be as small as possible if we're actually creating something that's useful. Okay? So what we have here, just to give you an idea of the ratio here, is a look at the variability in terms of variability in players when they're traded over the average variability we see across the league. And so what we did in terms of the modeling and picking the ridge regression is to get that so that it was as small as possible. In our case, we get it down to about 0.14. Okay? And again, we're using ridge regression. We get some shrinkage here to 0, but we're also dealing with the multicollinearity of line mates. Players that play together, we want to be able to pull out their effect. And so hence the reason for the ridge regression. So Gabe Desjardins, who does a lot of hockey analytics stuff, wrote this about building a team in terms of the Stanley Cup. You want to look for undervalued talents, right? You want to look for players that win face-offs, defensive play versus tough opponents, and penalties drawn. And I think part of what we're getting at here is some of those things. Okay? All right, some conclusions here at the end of the talk, right? The strength is we've got a fairly reliable system. Okay? It is dependent on the RTSS, and that is not optimal, obviously, and we're not getting everything. Right? We're not recording passes. We're not recording a lot of other things there that might matter. We do adjust for quality of teammates, quality of competition, zone starts, home ice. We got a very large sample size, and we're using a pretty robust method in ridge regression. Okay? The RTSS, as I mentioned, is a weakness. Okay? We have adjusted for some known biases. We don't have score effects here. Okay? So we've got only even strength. But in some cases, although 88% of the game is played within 2 goals, teams do tend to play differently if they're up by 4 goals. And that's still in here. So we need to think about whether or not to take that out. We don't see systematic team advantages. We do not necessarily see all of the players for a good team like Pittsburgh or Boston at the top of our ratings. Okay? Just a note here, because Gabe's going to give me 30 more seconds. Thanks, Gabe. Is that we hope to take the THoR and we hope to go live and have bi-weekly updates and be able to do that. And also to add our power play and power kill model, and to add rink effects, I think, to further get rid of some of the bias that we're seeing in that RTSS if it exists. I guess that's where I thank you since I'm out of time, and I'll be happy to take some questions.
So if there's questions, feel free to kind of come up and we'll have a mic here. But
how stable was the model from year 1 to year 2? I guess the question is, could you use this in the future for predicting player performance? I know it's very backwards looking.
So it's a good question. We combined the 2 years specifically to have enough sample size. I can go, and the slide I skipped over here, actually I've got an additional one here, that is last year plus a part of this year, okay? And we see a lot of the same names at the top. Obviously, we're going to see some differences, but And we're looking at a tail here, so it's not necessarily the best in terms of stability. But yeah, we do see some. I mean, the ideal is that we have in the model those players when they're switching teams. And we think we do pretty well at saying, okay, if this player goes from team A to team B, then yeah, we're going to capture that. We don't do perfect. Obviously, we weren't down at 0. But we think we do pretty well. Yeah, good. Thank you.
I think there's a question in the front here. Here you go.
Hi, I was curious, are you doing a positional adjustment or some sort of positional averaging for each grade, or basically you're doing comparison against the average player at every position?
We are looking at average at every position. So the relative to average is...
So, the question goes to, for example, if you're looking at, say, Tyler Kennedy, are you looking at him versus the average center or the
average player.
Average player.
Average player overall.
So there's a chance that there could be, I mean, if you looked at it from position to position, it might be slightly different in terms of that. Like,
almost surely it's going to be slightly different. And I would imagine that, I mean, the size of the defense is probably about a half a win. That the mean of defense sits about a half a win below the mean of offense.
I asked the question because if you look at something like basketball, when you look at this kind of thing, centers, if you just go against the average player, centers obviously come up higher because of just the nature of the position. That's why I asked the question. The other question I had was, now, in terms of how you're looking at it from a point of view, it's like, who do you think is there a position in particular that's undervalued in terms of, in your perception?
I don't know that there's a position that's undervalued, but I mean, I think Gabe's quote is right, that if we think about defensive defensemen, because we have so few metrics that really get at what they do, which is preventing goals, that sort of player ends up being very undervalued. Yeah, yeah.
Pass that down. Sorry.
Okay, so you're trying to minimize that parameter on the assumption that when players are traded, their value shouldn't change, right? So can you talk a little bit more about that assumption and why you think that's right?
You know, the idea is that hopefully we want to predict. I mean, if someone wants to acquire a player, right, we would, I guess, ideally you'd like to see, is their value going to be what I expect it to have been in the past?
But doesn't that, I mean, you're assuming that there are no teammate effects, right? If people are trading well, like trading to maximize synergy, then people's value should go up after trades, right?
I guess that's possible.
Okay.
Yeah, I mean, the idea is that if we think we're getting at their individual value, which is completely isolated from everybody around them, then what we should see is very little change. I think that's the assumption.
Okay.
Yeah.
Right. That's all we have time for today. But thanks again, Michael.
Thank you.